are you working? I think I may have screwed up.
You would never screw up.
Nope, it works.
Just throw away the last thing you did.
Okay, we're talking about molecular interactions. So we started out with ideal gas. Works great as long as the pressure is what? Really, really low, and the temperature is really, really, well, I guess it could be an or there. Temperature is really, really high, right? Because you want these molecules to be acting like what? Dots. You want them to act like dots. Okay, and then we started talking about the kinetic molecular theory of gases. Now you want them to act like what? These molecules. Clunk, clunk. Steel balls, essentially, right? Because then you can have collisions, exactly. Because then you can have volume. Because then you can have mass. Okay. Now we're going to kind of go a little bit more the way a lot of science is now. They start throwing in, I call them fudge factors. You just throw in some fudge factors. And we know the ideal gas law is PV equals nRT. Folks are easy to use. They're used to using it. It's straightforward. It's really easy to use. It's convenient. So let's stick with it. So let's throw our fudge factors so when we use the ideal gas law, we get the right answer for P. Who cares what the temperature is? Right? So you have a particular gas, you throw in its fudge factor, and boom. You get really close to the right answers. So that's kind of where we're heading today, I guess. So real life, that means molecular interactions, you can't avoid them. Okay. So let's go ahead and start here. We have this compression factor Z. Okay, big Z, not the collision frequency, little z, big Z, compression factor. What's this Vm? V with a little m on it. Oh, let's pick on Anna. What's V with a little m on it? Well, there's kind of a hint. I don't know if this is much of a hint, but we have PV equals nRT. If we divide PV by nRT, Anna, we should get what? If PV equals nRT, divide both sides by nRT, we should get, does anybody see it? We should get 1, right? Are you following? Look at this equation. Look at this equation. Very similar, except one has a Vm in it. What's Vm? Volume divided by moles. Vm is V all over N. That's what Vm is. What's a little m probably stand for then? Mole. Well, yeah, moles. So V is volume. V with a little m on it would be what volume? Would be the technical word for it. Molar volume, right? Well, thanks, Amanda. So, good luck.
Thanks.
So V with a little m on it. So really anything with a little m on it is molar. You can have a lot of different molar terms. You just divide by the number of moles. Okay. But if things are acting ideally and the ideal gas law works, you can plug everything into this relationship, and you better get 1, right? But you don't always get 1 if it's not acting ideally, right? Things are, if molecules kind of attract, Alice, okay, and stuff sticks to stuff. Stuff sticks to stuff. So in a real world, the pressure is going to be a little bit higher or lower in a real world situation. You can exacerbate it by being at different pressures, but stuff sticks to stuff. It'd be lower, right? Because stuff is kind of more interacting, more sticking to stuff. In a real world situation, the volume of that container, I know it sounds odd, but here you have your container. And there's so much space in it for the little guys to be flying around in. But if the molecules actually take up space themselves, the actual volume is a little bit less or a little bit more than that of the container. A little bit less, because the molecules themselves take up space. So and then you get the whole, the real problem though isn't the size of the container, it's these darn things interact and they repel under other conditions. So you're not going to get PV over nRT equal to 1 if you plug stuff in, especially at when things are condensing, for example, low temperatures. So you get, instead of writing a 1 here, they write a Z. And they replace the VM with, right, or the V over N with molar volume. So that's where that's a background of where this is coming from. Just how bad is the ideal gas law, or how good is it, right? Okay. And they're trying to, if you take a look at this first plot, potential energy. What's potential energy? Kathleen, what's potential energy? Yeah, stored energy is a good point for it. Just nothing that has to do with what is potential energy. You don't want any motion involved at all. It's all this stored stuff. It's this interaction stuff. It's nothing to do with motion. That's potential energy. Okay. So if you look at this plot, Sandy, we have separation and we have potential energy. Where separation of what? First off, separation of what? We're talking about gases, so probably separation between the molecules, right? So separation is how far apart they are, these two gas molecules. And I guess as the separation gets less and less and less, that means they're just getting closer and closer and closer. So where on that plot, if anywhere, Adriana, are these two molecules acting ideally? Where, if anywhere, would they be acting ideally? Like an ideal gas, acting like dots. The farthest away. The separation's the biggest, exactly. And it's kind of getting flattened out, and the potential energy is getting close to 0, right? Yeah, you don't want there to be any interaction, any stored energy. You don't want there to be any. So, yeah, that's where it would be acting ideally. So notice how, as they get closer and closer and closer, you get attraction. And then you get too close, right? They repel, and they start repelling quickly, right? You can't compress things once they get that close. Take a look at this next plot, figure 122. Now we're plotting Z versus our pressure. Z versus our pressure. And they just plotted it for different gases. So you pick a gas, like hydrogen, for example. Look at hydrogen's plot. And all they did is they just changed the pressure on you there. Oh, what are they keeping constant? They're keeping something constant. Right? They're changing the pressure, like maybe compressing it. But what are they keeping constant? Temperature. Those plots, Amberly, are called what? Isotherms. Right? So they're plotting isotherms for different gases. Just changing the pressure, keeping the temperature the same. And what's the effect on your Z there? Okay. So if it's acting ideally, Z should be what again? Everybody? Z should be 1. So it looks like hydrogen. Does hydrogen, well, I guess hydrogen's never really 1. How about, is hydrogen always above 1 or below 1? It's always above. So if you go back and you look at this thing, why would, I don't know if there's much of a hint here though, why would hydrogen, the gas hydrogen, always give numbers for Z bigger than 1? Now that means P or V, oh man, it's too big, right? Why? It's too big. I think the pressure is the easier one to see. What could be going on between hydrogen to cause the pressure to be bigger than what you'd get by having dots? Hydrogen doesn't attract. Hydrogen, well, we can't have bonding because we're not going to make the temperature that cold. We're not going to make liquid hydrogen. Hydrogen they bounce apart. Hydrogen repels. Hydrogen repels. All right, because just think what hydrogen is. Essentially 2 protons, right? I mean, there's not much to attract. For stuff to attract, you just need more stuff. Methane is going to exhibit attractive properties to other methane molecules, but not hydrogen. Hydrogen's always repelling. Oh, yeah, look at methane, right? It gets below 1. So when you're above 1, what type of forces must be going on between these molecules in general? Overall? Attractive or repulsive? Repulsive, right. And I guess if Z is less than 1, what must be going on is attraction forces. Okay. Okay. Oh, what are we supposed to call those forces? Like attractive forces between molecules. What was the technical word for that? Intermolecular forces, right? So then remember we had some in Gen Chem, like van der Waals and things like that. Okay. So here's our first. We had the ideal gas law. We called it an equation of state. Why did we call it an equation of state? What was the big deal with that, Rob? Equation of state. Ooh. What does that mean?
Something like the equation that represents the behavior given a certain pressure, volume, temperature.
Perfect. You hear what he said? It just describes the behaviors. You can talk about predicting anything. Pressure, volume, temperature. You just have to throw in some parameters, and that equation is going to predict and tell you what's going on with the other parameters. So here's another one. The Virial equation of state. Except you've got, again, they want it to kind of stay in this ideal gas law form, but they have some B's and C's in here. Then they have a table. Okay, now first, you got to get these names down. B is the first virial coefficient. C is the second virial coefficient. I don't know why, but I just have a table of the second virial coefficients for some gases there. Okay. So when they do these sorts of expansions, and it's mathematical, we're not going to do the proofs or anything, but the first term in all these expansions, they just get less and less and less important. So you can really avoid a lot of stuff. That's why they have the dot, dot, dots. I'm sure there's a D, but it's so small it doesn't even interact. There's no big deal. What could be, you're talking about gases, and they're interacting. What could be going on here to have a first term, a second term, a third term? Well, the first term is just, okay, these two guys attracting, sticking together. Essentially, we're talking about collisions. So you can have a two-way collision. Then you could have the next possibility would be a three-way collision. The next possibility would be a four-way collision. So these are getting less and less probable, big time. So that B is the pairwise collision, pairwise interactions. Right? I guess the collision might be too strong of a word because they're just interacting, they're just flying around each other. So pairwise interactions. What would be the word for three-way? Triwise? Right? Something like that. Three-way interactions. Okay. And we mentioned boil temperature. I don't know if boil temperature is just where in this plot up here with Z is where there isn't any slope. So nothing's interacting, right? There aren't even these two guys that are not even there aren't even any pairwise interactions. It's just acting ideally. So if you get to this boil temperature, right? Anything above it, make it a little bit hotter. It'll stay intellect ideal. That's just the name with the boil temperature. It's just, hey, when can we start just using PV equals nRT and not worrying about this, right? If you're below your boil temperature, you better look up at the table and get these virial coefficients. But if you're above it, who cares? You don't need it. Okay? That's where that's kind of coming from. And then what's down here? I want to take a look at this next plot. Here he is. What did I want to say about him? Okay, we already said what an isotherm was. I think someone told us. Emily, what was an isotherm again? Temperature doesn't change. Right. Okay, so let's follow one of these plots here. Oh, I don't know. It's the guy with the dots on him. Let's follow that isotherm. Hey, no, you're fine. Let's follow the isotherm with the dots. So what we're doing is we're having an isotherm and pretty much just reducing the volume. Pretty much just a piston and you're compressing it. Oh, then what's going to go up then if you're keeping the temperature the same? The pressure. All right, that's what happens, right? The pressure's going up on this guy. Okay, so we're at A, right? And we keep compressing it. We get to B, right? But it's resisting. It's resisting. And then you get to C. Something weird happens, doesn't it? You get to C, and you're compressing, but shoot, nothing's pushing back on it. Well, it's pushing back, but it's not increasing. Right? The pressure's not increasing, and you're compressing it. How? It actually happens. Right? You've jammed this stuff into such a small space, such a high pressure, that it's starting to what now? Condense. Right? Because you know a liquid takes up a heck of a lot less space. So it's condensing until it all turns into, at E, and look how the pressure just skyrockets. So at E, it's all completely a, because what can't you compress? You can compress gases, but you can't compress liquids. That's why hydraulics works so great. You can't compress liquids. So that's why the pressure, it's all liquids at point E. It's all liquids. So you can't compress it anymore. So the pressure just skyrockets. Okay. So you're messing around with this. So now you make the temperature of your little apparatus a little bit higher. Keep doing the same thing again and again and again and again. And pretty soon what happens, look at this. You get to some point, they have a little star there. See that little star? If you try to do this experiment above whatever temperature that is for this gas, looks like it's around 79 or so, you never get the what? You never get the what state? You never get condensation to happen. You never get a liquid. It can't exist. It doesn't exist at any temperature above that little star. A liquid can't exist above that temperature. Why? Now they call it the what temperature? Critical temperature. Right? They call it the critical temperature. Every gas has its own critical temperature. It actually happens. Why? Why would it? What's going on that you couldn't? The temperature's so high you can never form a liquid. It's what? Yeah, it's kind of yeah. You're getting there. Things are just moving so fast because isn't that what temperature is? You crank it up so high, things are moving so fast they just can never condense. Can never stick together. Things are just moving too dang fast. So if we took a look at, let's see if we can get this to work. This is heating from below to above. Wow. they're heating it up.
The meniscus disappears, and only diffraction irregularities are present due to temperature gradients. Here, the forces due to molecular movement overcome the surface tension, and the separation between liquid and vapor disappears. Above the critical temperature, only the gaseous phase exists. A gas above the critical temperature cannot be condensed into a liquid, since the molecular attractive forces are dominated by the rapid molecular motion.
Isn't that funky? You can't even see anything anymore. And you can't, and that makes sense. And the whole thing disappeared. It's all a gas. Well, supercritical fluid is a trick. That's how do you decaffeinate coffee? How do you now, coffee is a big deal, right? Is anybody a coffee drinker? I mean, it's like an addiction. And I forced myself to start because it doesn't matter where you go. There's the coffee, right? Go to any meeting, go to any whatever, there's the coffee. They don't give you the juice. Sometimes they don't even have water. So anyway, force myself to start drinking coffee. And now, you start liking it, and it almost becomes an addiction. But man, everyone is really strong in their coffee. You can't be, so let's get some decaffeinated stuff. Big money in this. But you can't screw up the taste. That's the whole big deal with coffee. Now, coffee drinkers, you can't mess with that taste. And we're talking about getting an organic compound out of coffee. You can't, and you don't want any traces of that organic compound. Now, organic, how do you do it? You got your little, dump some solution, right? You can do this whole thing, and you release the gas. I mean, you can put it on a huge, big factory scale. Forget it, man. You're going to screw up the taste of that coffee. Use a supercritical fluid. And what happens, carbon dioxide is a supercritical fluid, dissolves caffeine fantastically. Like dissolves like. I don't know why this works, but it works. They found that it works. And the nice thing about it is that what do? Just warm the stuff up. The CO2 just turns into a gas and leaves. And the coffee's coffee still, except there's no caffeine. Right? It's an easy way to decaffeinate coffee. So there are actual uses for this stuff. If you go cooling below, so now we're going to start above the critical temperature, and we're going to let it cool.
As the temperature decreases, the meniscus reappears at the critical temperature. The molecules in the gas move more slowly, allowing the attractive forces between the molecules to become dominant. At this point, separate liquid and vapor phases form. Note that the thermometer is present only to indicate increasing and decreasing temperature and an approximate range for the critical temperature.
I don't know, man. For something that's kind of cool like that, the guy could be a little more excited, but it's okay. That's okay. All right. So we've had the virial equation of state. Find the fudge factors B and C, where B represented what kind of interactions? Essentially, two-way, right? So what's probably going to be a bigger number, the B or the C? The B's. And if you don't find a table for C, great. The table for B is more important anyway. Okay. And these expansions. Another equation of state. So we've had the ideal gas, we've had kinetic theory, we've had the virial. Now we've got van der Waals. Where are the fudge factors, Kathleen, in the van der Waals equation of state? The B and the A. So that means if you're going to use the van der Waals equation of state, Sandy, you've got to look up the B and the A for what? For what? The gas. You don't memorize this stuff. You look it up, and all that stuff is in the book. For helium, you got to plug in the B and the A for helium. Okay. Now there might be some. Let's see. The pressure. Kind of take a closer look at this. This might give you some hints for the homework. Take a look at this first one. The pressure equals something minus something. So the pressure is being reduced, right? So this second pressure, this A times N over V squared, is the reduction in pressure due to what? The molecule's what? In effect, this is causing the pressure to be reduced. Stuff sticking to stuff. Except we're not supposed to say that. We're supposed to use the A word. Attraction. Right? Due to attraction. So that's the reduction in pressure due to attraction. So that's the little A guy becomes important there. Okay. Now, what did we say about the volume? The volume is being reduced. Right? That's the V, that big V, that's the V you plug into the ideal gas law. They're trying to make it, same format. But it needs to be reduced a little bit. N times B. What's NB? Is that taking into account? Why is the volume a little bit less than what it's supposed to be? Why is it a little bit less than the volume of the container? Well, because the molecules have a what themselves? A volume. They're taking up some space. So that little NB is the volume of the little NB, the volume of the molecules themselves. Volume of the molecules. Okay. Okay. Reduced variables. We kind of, if you take the temperature and you divide it by your critical temperature, you get, all they're doing is they're trying to, let's start here. Reduced variables. You divide, to get the little r, you divide it by its critical temperature, right? To get the reduced pressure, you can divide it by its critical pressure. But then they have some other equations in here, and the reason why they're starting to talk about TR, reduced temperature, PR, reduced pressure, VR, reduced volume, is if you could have a reduced temperature, reduced pressure, reduced volume for all these different gases. Helium and neon, for example, right? If they have the same reduced temperature, reduced pressure, and reduced volume, they are in the same state. That's the principle of corresponding states. If two gases have the same reduced everything, reduced temperature, reduced pressure, reduced volume, they're in the same state. Okay? And that's kind of odd. I think why they're messing with it is they're trying to get, you don't always have to use van der Waals. It's kind of like another equation of state thing, but there's no little fudge factors. Except there is. Why would this all of a sudden work? There's got to be fudge factors in there. The reduced variable, it's inside. The fudge factor is hidden inside the reduced variable. You're getting close. Where's the fudge factor in here? Something you're getting from the table. The critical temperature. So you're sticking in 3 fudge factors now instead of 2. I think it's getting worse, but whatever. Right? So that's how it is. Okay. All right, so we've got some exercises. Ooh, yeah, there aren't any. Okay. No problemos. So our first one. Find the pressure exerted by 1 mole of C2H6. What is that? Ethane? Behaving as a perfect gas. I'll just start there. Well, that means you're supposed to use what equation of state? What equation for? Just use PV equals nRT, right? It's supposed to be acting like a perfect gas. So we'll just use that one for that one. Do we have them all covered? They want to know the pressure, so we're going to solve for that one. They better have given us a V. Did they give us a V?
Later, the 1 and 2.
Oh, yeah. Thank you, sir. There's my V.
There's the first one, the 22.41 liters.
Oh, you're supposed to do it twice.
Yeah, unless you don't want us to.
Thank you, sir. He's reading this a lot more carefully than I am. All right, there's my V. If we can do it for the first one, we can do it for the second one. Let's just look at this first set here. This, what do you call that? Little I. Let's do it for the first part. So there's my V. So I've got that one. They have to tell you the number of moles. You see it? Yeah, it's a 1. We know what the R is. Just look it up. Make sure you pick the one that's the most convenient. And they had to have told us a T, and they did. All right, so no big deal. All right, which R are you going to pick to make your life the easiest? Which R? Now, if you do the 8.31, I like the one with liters ATM because you're already in liters, right? Use the 0.0821. I would for that first one anyway. Maybe for the next one. Well, even for the next one, 100 cubic centimeters is how many milliliters? They're the same, so it's 1 milliliter a cubic centimeter. So 100 cubic centimeters would be 100 milliliters, which is how many liters? 0.1. So I would probably use the same R in both of those guys. Okay. Anyway, that's how you handle Part A. Part 1 of Part A, I guess, right? And then they want a van der Waals. Okay, so let's find that equation. Where did it go? Here it is. Okay, that's really nice. They didn't ask for volume, because just think of all the rearranging you'd have to do there, but they wanted pressure. It's already written in that form. Right? Okay. We know the N, the R, the T, we know the volume, right? Looks like we're gonna get the A and the B. Google. Yeah, that would work. Oh, table 1.6, yeah, it might even be faster than Google. But that's okay. Which one would you use? Would you use the first one or the second one? Well, you still have to find little n for this one, don't you? Because Vm is what over what? Volume over n, right? Vm is V over n. So you still have to worry about little n on the second one. But that's not why I would pick the second one. Because if you're going to use the first one, what else would you have to find? You see there's something in there. V, that little V. Right? What the heck is that little V? It looks like a velocity, doesn't it? I didn't use that first one, so what the hell is it? What would that be? That little V. Yeah, what does the book say that little V is? The big hint would be what the units of A are. That would really tell you what little V is. Oh, really? So this is a typo?
I'm still trying to find it.
This guy should be a big V?
Yeah.
Really? What page is that on? Page 33. Ooh, we found a typo. I bet I've never used that first one, so I never really cared. Page 33. Oh my goodness. That's a big typo. All right. Okay. So then it doesn't matter which one you use, right? Okay. What was the next part? Van der Waals. Oh, that's it. All right. Van der Waals. And then you have to do it again in part 2. Okay. And I guess there should be a second part to that, but I guess it really doesn't matter. Oh, I'm going to add a part. The part that probably makes the most sense, a part 3. Under which condition? Because you went through all this work, you should look at it. Under which condition did the Van der Waals and ideal gas give, what would be more interesting? Similar results? I think that'd be the similar results, right? When is the ideal gas law working? So you don't have to go through all this work of finding little a and b, right? Under what conditions did the Van der Waals gas give answer closest to the ideal? Now, you should have a rough idea what it should be. We've talked about it. We've never proved it, though. So, okay. Estimate the critical constants of a gas. So now we're taking a look at this next one. Estimate the critical constants of a gas with Van der Waals, oh yeah, blah, blah, blah. Critical constants. What are those? There's a big hint up here. Yeah. All right, Emily? Because they're saying, look, here's little a, here's little b. Give us the critical constants. Well, critical is kind of a hint, but so are all these equations you're given, right? So they want TC, they want PC, they want VMC. How would you say VMC in words instead of VMC? Critical molar volume. Yep. So that one's not so bad either. Are you guys with me so far? How about 22? Oh, that's a good question. You see Rob's question here? We want to get TC, PC, and molar volume, critical molar volume. You got to plug in a number. The A and the B they told us, but you got to plug in an R. Looking at the A's and the B's that they gave you, which R would be the most convenient? Which R would be the most convenient? The 0.0821. Otherwise, you can have a lot of converting to do. Okay. Take a look at this one. This one's going to be to write some stuff down here, I think. Okay. Yes, that's it. See if we can figure this one out. See, I don't know if you've noticed, but in a lot of these problems, and there are some big equations. So it's just like in earlier chemistry classes. If an equation has 5 variables, and these are going to be a lot more than 5 variables, but if it has 5 variables, the problem has to give you 4. If it has, 8, it's got to give you 7. So I just start listing all this stuff out, whether I know where I'm going or not. And it makes it more visual for me anyway. And they want us to calculate the compression factor. So I wouldn't write compression factor equals. I would write equals question mark. I would write what? What's the compression factor? What's the symbol for it? Z. Put in the Z. It's going to be a lot more guiding what you're after. Right? And to me, again, I may not know where I'm going, but let logic dictate what to do. If you wrote Z equals question mark, the next logical thing would be to go look for what? An equation with Z in it, right? So, where is it? There it is. Z is PVM over RT. Okay, so we're close. VM is 12% larger than that predicted by the ideal gas law. Now this is the thing that we have to get over, is this stuff, all this stuff, I mean, even in that darn van der Waals, that V is the volume predicted by what law? The ideal gas law. That P, well, not the little p, that's why they kind of gave you a little p, but that T is the ideal gas law temperature that you're plugging into PV equals nRT. All those guys are the PV equals nRT ones. At least they're being kind of consistent that way. So it's like that VM. That's the molar volume that you would use in the ideal gas law, V over N. Okay. So, same thing here. These are ideal gas law numbers. But they're saying, okay, look, your pressure, it's not acting ideal. Here's your fudge factor. So how do you change this VM to reflect what this thing just said? Like you could multiply it. What I'm saying is 12% larger. If you said VM is, that's where you put the equal sign, 12% larger than that of the ideal gas law. What number would you put there? For some reason I can't be seeing this in my head. How do you do this? Something is it 0.12 or 0.88? All right. This is 12%. Well, we can just plug in some numbers and see. If I think my brain says I'm going to get the right answer if I do this. Let's plug in some numbers and find out. If you plug in 100 plus the 12%. Yeah. So the real is 12% larger. So yeah, because it'd be the 1 plus the 12%, which would be 1.12. Yeah. So here's our real is 12% larger than the ideal, right? Okay. That makes sense. So what are we going to put in right here for this guy? So we need to find that VM. How are you going to find it? All right. We're going to have to use the ideal gas law to get it. All right. Whatever you get, plug it into here, because then plug it in and calculate our Z. All right. Because this is supposed to be the ideal gas law, molar volume. Well, that's PV equals nRT. So what do we know everything, but what do we use for N? Well, you could assume it's 1. Really, you just pick one, because it's molar volume. If you pick N equals 1, it's kind of the easiest, because then you can forget about it. But if you pick N equals 2, well, then you calculate your molar volume. Just, molar volume is molar volume. It doesn't matter how many moles you have. You just pick one. The easiest one to pick is 1. It's less math. Okay. Still don't quite see that. We'll see if you get the right answer in the back of the book. Oh, I think how I was seeing this. The ideal, because what we're going to do is we're going to calculate the ideal. All right. So that's how I was thinking of this. Is because this guy I calculate. Right? So whatever I get, multiply it by 0.88 and I'll have VM. But that's how this way should work too. The way you guys are doing it. Okay. We're about out of time. But check out these and be glad to help you out. Yeah, we have lab on Monday. Check out the schedule to see what we're doing. I don't even have my syllabi. What does it say? Lab Monday, we're doing... So just bring your lab book there, because everything's in there. We're going to mess with graphical analysis and equation editor. Okay. Oh, you will.